Today we'll be starting notes on 1.1, which has to do with moles and molar mass. So the first unit we deal with is atomic structure and properties. So today we're going to look into formula and molecular mass, the mole, and Avogadro's number. So formula and molecular mass are both the sum of the masses of the atoms in a chemical formula. Ionic compounds, they exist as a network solid with an arrangement that's called a lattice structure, and it's a combination of positive and negative ions. So we don't really call ionic compounds molecules. They don't form really any sort of bond. So we call an ionic bond a bond, but really it's an attraction between a negative and positive ion. So it's an electronic attraction more than it is a bond. Bonds typically mean that electrons are being shared. So ionic compounds do not form molecules. They form what we call a formula unit, but the idea is the same. So NaCl, sodium chloride, is a network solid where we have sodium ions and chloride ions stuck together in a 1-to-1 ratio. Ionic compounds do not always have a 1-to-1 ratio. Basically, the ionic compound has to have a neutral arrangement. So the positive charge has to equal the negative charge. So if we have something with a +2 charge and a -1 charge, you're going to need twice as many -1 charge ions to balance out that compound to make it neutral, and that will give us its formula unit. So again, formula mass refers to the basic unit in a network solid. It is the mass of one of these basic units, whereas a molecular mass is used to refer to molecules that exist independently, and it's the mass of one molecule. So formula units and molecules are similar. It's just formula units refer to ionic compounds, whereas molecules refer to covalent compounds. The masses are found basically the same way, and that's by adding up the atomic masses of those compounds which make it up. So for example, we can find the formula mass of magnesium hydroxide. So magnesium is an element on the periodic table, so you can pull one up. It's going to be in group 2. It's element number 12. So based on what we know about charges, magnesium is going to form a +2 ion. Hydroxide is not an element on the periodic table. Hydroxide is a polyatomic ion, which hopefully you remember as OH with a -1 charge, okay? So we have a +2 and a -1, which means we're going to need twice as many hydroxide polyatomic ions than we have magnesium. Okay, so that's how we get the MgOH2 formula. There's one way that I like to show this, and so that's by writing our ions. I'm not the best at writing on a computer, sorry. Mg +2, and then we have our OH -1, and this is going to stay as a unit together. So to balance out charges, I like to do just a simple crisscross method. So do this, so then when we get Mg with a 1 subscript, which we don't show, and then OH2, and then we would reduce. So for example, if we had 2 and 4 here, we would reduce to 1 and 2. But here, we are already reduced because 1 and 2 can't be reduced any further. So that's how we find the chemical formula, or really molecular, or not molecular, see I do it all the time, formula unit of magnesium hydroxide. Okay, there we go. So we have one magnesium atom, so 1 times the molar mass of magnesium, which is 24.31 atomic mass units, AMU. And then we have 2 O atoms, so remember this 2 is going to distribute, so it applies to both the O and the H. So that's 2 times 16 AMU, which is 32 AMU, plus 2 hydrogen atoms, which is 2 times 1.01, which is 2.02 AMU. If we add all of these together, we get a formula mass of 58.33 AMU, atomic mass units. Now, atomic mass units are really great for describing the microscopic world, but usually we don't measure out atomic mass units because they are so small. So for example, when you are in the lab, you don't have a scale that is sensitive enough to measure out AMU. So that's where Avogadro's number, which is shown also as N with a subscript capital A, Avogadro's number. So that's where Avogadro's number is going to kind of come into play. So Avogadro's number, 6.022 times 10 to the 23rd per moles, or mole to the minus 1, is basically a number of something that we can have. Okay, so 1 mole is equal to 6.022 times 10 to the 23rd numbers of something. So Avogadro's number is kind of, or the mole, is kind of like a dozen. Okay, so 1 dozen of anything is equal to 12 of those something. 1 mole of something is equal to Avogadro's number of something, which is 6.02 times 10 to the 23rd. So if I had a mole of eggs, I would have 6.022 times 10 to the 23 eggs, which is a lot of eggs. If you had that many coins, it would basically cover the surface of the Earth with a 2-meter depth. Okay, so that's a lot of coins. If you had a mole of grains of sand, it would cover Texas, and it would have a depth of 15 meters, okay? So a mole is a very, very large number, but we need this large number in order to work with the macroscopic world that we deal with and see, okay? So we can't have a beaker that's filled with 1 water molecule. Okay, we wouldn't be able to observe it or see it or anything, but we can have a beaker filled with 1 mole of water molecules, and that 1 mole of water molecules will actually be equal to the molecular weight or molecular mass of water, except for the unit this time isn't in AMU, it's in grams. Okay, so Avogadro's number provides a connection between the number of moles of a pure substance or sample and the number of particles or units in that sample. So when we're talking about moles, we no longer use the unit AMU, atomic mass units. That's on the microscopic. That's the microscopic unit that we would use. In this case, we would be able to use a macroscopic unit of measurement, which in this case is going to be grams. Okay, so 1 mole of neon atoms is equal to Avogadro's number, 6.022 times 10 to the 23rd neon atoms, which is going to be equal to 20.18 grams. So if you pull out your periodic table, look at neon, it's element number 10, the atomic mass of neon is 20.18 AMU. Okay, so 1 atom would weigh 20.18 AMU, atomic mass units. 1 mole of neon atoms would weigh 20.18 grams. You'll also see it written as grams per mole because there's that many grams in 1 mole. Okay. Same thing with chloride ions. If we had a mole of chlorine ions, chloride, we would have 35.45 grams of chloride ions. So the mass of 1 mole of any element is going to be equal to its atomic mass on the periodic table, but the unit is going to be in grams. Let's see what else. It's a fundamental unit for counting particles on the macroscopic level, so that's how we relate what we can actually measure in the lab to the number of atoms, which then we can relate to the chemical equation when we get to stoichiometry. And it allows us to draw quantitative connections between macroscopic experiments and atomic level chemical processes. So if we want to find the molar mass of CO2, carbon dioxide, its molecular weight is going to be 12.01 AMU plus 2 times 16 AMU, so carbon and 2 oxygen, which is 44.01 AMU per molecule. If we had 44.01 grams of CO2, we would have 1 mole of CO2. So the molar mass is measured in grams or grams per mole. So 1 mole of CO2 would weigh 44.01 grams. And again, 1 mole is going to be 6.022 times 10 to the 3 CO2 molecules. and those would weigh 44.01 grams. So we write grams per mole usually when we're doing conversions. So let's say you need to find the number of atoms, things like that. You would have to go from grams to moles, which is why we like the gram per mole unit for molar mass. So here's an example. We're converting grams to moles. We want to know how many moles of sodium chloride there are in 48 grams of NaCl. So this is where we're going to start to use dimensional analysis. So if we start with 48 grams of sodium chloride, we would divide by the molar mass of sodium chloride. And I know to divide because I want to cancel the grams unit and ultimately ends up with moles. So right here, grams is in like our numerator. So to cancel that unit out, it needs to be in the denominator. So that's why I know to put grams on bottom, and we'll have 1 mole in the numerator to end up with 1 mole. So if we take 48 grams times 1 divided by 58.44 grams, which I get using the periodic table, 1 sodium ion plus 1 chloride ion. Those weights, formula mass would be 58.44. And we get 0.82 moles of sodium chloride. So here you can see where my grams cancel out and we end up with moles. Here, we're starting with moles and going to grams. So how many grams of C2H6 are there in 18.7 moles of C2H6? Okay, so here we're starting with moles. So for our conversion, for dimensional analysis, what needs to be in the numerator and what needs to be in the denominator? We want to cancel out moles, so ultimately we want moles in the denominator. So that grams per mole, we're actually going to be multiplying by, because per mole means in the denominator. So we're going to multiply by 30.08 grams divided by 1 mole. And we get 562 grams of C2H6. Where did this 30.08 come from? It comes from the periodic table by adding the molar mass, which is the same thing as the atomic mass numerically, just different units, of 2 carbon and 6 hydrogen. We can also convert grams to molecules, and we do this by going through moles. So I will share with you, or I shared with you over the summer, but I can do it again, just this little flow chart of what to do when you're looking for stuff. And at the heart of this flow chart is moles, because we can compare microscopic things through moles if we start with a macroscopic. So it's kind of like the bridge between what we can measure and what's going on the microscopic level. So if we have 56 grams of a pure sample of water, first thing we have to do is find how many moles of water is that. We can't compare grams to molecules right away. We have to go through moles. So I'm going to be using molar mass again. Here I'm going to want to be canceling out grams. So I'm actually going to be dividing by molar mass. We want grams in the denominator and moles on top. So 1 mole of H2O weighs out 18.02 grams of H2O. So that gives me my number of moles. From here, I can go from moles to molecules. So remember, mole is like a dozen, okay? So if I had 1 dozen eggs, I know that I have 12 single eggs. If I have 1 mole of H2O molecules, I know I have Avogadro's number of H2O molecules. So here I want to cancel moles. That's what's in my numerator. So moles is going to be on bottom. In 1 mole, I have 6.02 times 10 to the 23rd molecules. And I always abbreviate molecules as MLC, just so I don't confuse it with mole. Okay, so then I go from grams to moles. You can see how all my units cancel out. And we find out that we have 1.9 times 10 to the 24 molecules of H2O in that 56 gram sample of water. Okay, so that's all I have time for this video, and I will make a part 2 video for you to watch. So stay tuned.